Hello everyone, welcome to Brain Blitz Audios. In today's episode of NEET Preparation, we'll be looking at previous year questions of chemistry in medical entrance examinations in India. Today, we'll be dealing with the chapter Structure of Atom. This is the second chapter in the Grade 11 syllabus for CBSE in chemistry. Let's begin with the first question. The de-Broglie wavelength associated with a particle of mass 10 raised to minus 6 kg moving with a velocity of 10 meters per second is one of the four options. We need to find out which of these is the right option. So we're given mass 10 raised to minus 6 and the velocity is 10 meters per second. We need to find out the de-Broglie wavelength. So the de-Broglie wavelength is given by the formula lambda is equal to h divided by mc, where this h is the Planck's constant. On putting the values, Planck's constant has a value of 6.63 into 10 raised to minus 34 divided by the mass is 10 raised to minus 6 into the velocity here is 10. So now, upon looking at the denominator, we find that it is in the form 10 raised to minus 6 plus 1. So lambda will be 6.63 into 10 raised to minus 34 divided by 10 raised to minus 5. And now we have 10 raised to minus 34 divided by 10 raised to minus 5, which will be 10 raised to minus 34 minus of minus 5. So that is 10 raised to minus 34 plus 5. So it'll be 6.63 into 10 raised to minus 34 plus 5. So our answer will be lambda is equal to 6.63 into 10 raised to minus 29. And that is equal to option D. Note that the wavelength is expressed in meters, the SI unit for length. So our value for lambda would be 6.63 into 10 raised to minus 29 meters when we have the given mass and the given velocity. Let's move on to the next question. Which of the following element is represented by the electronic configuration 1s2, 2s2, 2px1, 2py1, and 2pz1? So over here, unlike normal electronic configurations, you find out the existence of px, py, and pz. What are px, py, and pz? So we all know that p is a suborbit in a given shell. The suborbit p further is divided into 3 orbitals. And these 3 orbitals are px, py, and pz. So since the second shell has 2s and 2p, we've just written 2p into 3 orbitals, 2px, 2py, and 2pz. And the number in the superscript implies that there is 1 electron each to each of the orbital. So why is this scenario taking place? This has to do with Hund's rule for maximum multiplicity. If 2 or more orbitals of equal energy are available, the electrons will occupy them singly before filling in pairs. So if there are 3 orbitals, first they will fill each orbital by 1, and then they would fill the second place. So 1 orbital has space for 2 electrons, and suppose we have 3 orbitals, then the first electron would fill here, the second would fill like this, and the third would fill like this. And only then will the next electron fill out one of the orbitals completely. So that is the scenario given here. So in order to find out which of the following element is represented, we need to count the number of electrons. So 1s2, that means 2 electrons, plus 2s2, that means 2 electrons, plus 2p1, 2px1, that is 1 electron, plus 2py1, that is 1 electron, plus 2pz1, that is 1 electron. So it is 2 plus 2 plus 3, which is equal to 7. So the number of electrons is 7. So since the atomic number Z is equal to the number of valence electrons, we just need to find out which of these has an atomic number of 7. Option D, sulfur, has an atomic number of 16. So it's incorrect. Option C, fluorine, has an atomic number of 9. So it's incorrect. Option B, oxygen, has atomic number 8. So that is incorrect. Therefore, the right answer is option A, nitrogen. It has atomic number 7, and the electronic configuration of nitrogen is represented as 1s2, 2s2, 2p3, and which can further be divided into the configuration given here. So option A, nitrogen, is the right answer. Next question. Quantum numbers of an atom can be defined on the basis of A, Hund's rule for maximum multiplicity, B, Pauli's exclusion principle, C, Aufbau principle, D, Heisenberg's uncertainty principle. So quantum numbers, it is a set of numbers representing electronic configuration. And in this set of quantum numbers, every electron has a unique set of quantum numbers. So Pauli's exclusion principle states that no two electrons will have the same set of quantum numbers. Even the electrons in the same orbital will have opposite spin. So their spin quantum numbers will be different. So quantum numbers of an atom can be defined on the basis of its uniqueness, which is provided by option B, Pauli's exclusion principle. Option A, Hund's rule for maximum multiplicity, implies that the electrons are filled singly into each orbital before filling doubly. And then the Aufbau principle states that the filling of orbitals follows the order 1s, 2s, 2p, 3s, 3p, 4s, 3d, and etc. And Heisenberg's uncertainty principle states that you cannot measure the momentum and the position of an electron simultaneously. So option B, Pauli's exclusion principle, is the right answer. Next question. The spectrum of Li2+ is similar to that of hydrogen, beryllium, helium, neon. The spectrum here refers to atomic spectrum, and this atomic spectrum is the spectrum of the frequencies of electromagnetic radiation emitted or absorbed during transitions of electrons within an atom. So when an electron moves from a lower energy level into a higher energy level, the frequency that is emitted is recorded as an atomic spectrum. This atomic spectrum is reliant on the number of electrons. So elements compounds or ions with the same number of electrons would have the same atomic spectrum. So over here, we have the spectrum of Li2+. So lithium has an atomic number of 3. So there are 3 valence electrons. So the charge given is 2+. 2+ indicates a loss of 2 electrons. So Li2+ will have 3 minus 2 electrons. So that means Li2+ has 1 electron. We need to find out which of these has 1 electron and 1 valence electron. So let's look at each of our options. Neon has an atomic number 10, so it has 10 valence electron. Then helium, it has 2 valence electrons. Beryllium has 4 valence electrons. And hydrogen, the first element in the periodic table, will have 1 valence electron. So the spectrum of Li2+ will be similar to that of the spectrum of the element having only 1 electron in its valence shell, which is hydrogen. So option A is the right option. Next question. The azimuthal quantum number defines E/m ratio of electron, angular momentum of electron, spin of electron, magnetic momentum of electron. Option D, magnetic momentum of electron. This is represented by the magnetic quantum number. And this magnetic quantum number is represented by m, and it has a value of minus L to plus L, where L is the azimuthal quantum number. So since magnetic momentum of electron is represented by the magnetic quantum number, option D is incorrect. Option C, spin of electron. This is defined by another quantum number, which is the spin quantum number. Now this defines the spin of an electron in an orbital. So option C is incorrect. Option A, E/m ratio of electron. This quantity is not defined by quantum numbers. This quantity, E/m ratio, was used by J.J. Thomson in order to discover the electron. Option A is incorrect. Now, since we've defined 2 quantum numbers, it pays to know what the third kind of quantum number, that is the principal quantum number, represent. So the principal quantum number, that is n, this defines the energy level of electron. And so it is represented by n, which is equal to 1, 2, 3, etc. And that gives rise to the K shell, L shell, M shell, etc. So the remaining quantum number, which is the azimuthal quantum number, must define option B, the angular momentum of electron. Azimuthal quantum number is defined by L, which is equal to n minus 1. It has the values of 0, 1, 2, 3, which is discovered so far, and those represents S, P, D, and F suborbits. Next question. The quantum number m of a free gaseous atom is associated with A, effective volume of the orbital, B, the shape of the orbital, C, the spatial orientation of the orbital, D, the energy of the orbital in the absence of a magnetic field. So quantum number m would represent the magnetic quantum number. And so this will tell you the number of orbitals present. So for example, if I have a magnetic quantum number m, which is equal to -2, -1, 0, 1, and 2, that means it will have 5 orbitals in that particular subshell. Now, if you look at our first question, the subshell 2p had 3 orbitals, px, py, and pz. And the reason why they were aligned as such is that px, which is dumbbell shaped, is acting along the x-axis. Py, another dumbbell shape, acts along the y-axis, and pz, the third dumbbell shaped orbital, acts along the z-axis. So this effectively represents the spatial orientation of the orbital, which is changed and which is represented by the magnetic quantum number. So therefore, option C, spatial orientation of the orbital, is the right answer. Quantities such as the effective volume of the orbital, the shape of the orbital, and the energy of the orbital in the absence of a magnetic field all remain the same. So therefore, they are incorrect. And this quantum number changes from -L to +L. And so it is associated with the spatial orientation of the orbital, which is different for different orbitals within a specified subshell. Next question. For the principal quantum number, n is equal to 4, the total number of orbitals having L is equal to 3 is. So we're given the options 3, 7, 5, and 9. So we need to find out the total number of orbitals having a principal quantum number n is equal to 4 and an azimuthal quantum number L is equal to 3. So n is equal to 4 implies that this subshell is in the fourth shell. And L is equal to 3 implies that this is an F subshell. So our subshell in question is for F. F subshells usually have 7 orbitals. So for the particular quantum numbers n is equal to 4 and L is equal to 3, the total number of orbitals is option B, 7. And the reason why is that we have an f orbital, and an f orbital usually has 7 orbitals. So the orbital in the subshell in question is for F, and it has 7 orbitals inside it. Next question. The isoelectronic pair of ions or atoms in the following is, and so we have 4 pairs given here: Cl2O3 and ICl2 minus, ICl2 minus and ClO2, IF2 plus and I3 minus, and finally ClO2 minus and ClF2 plus. So isoelectronic means that both these compounds will have the same number of electrons. Let's look at each option. In option A, we have Cl2O3. Now, chlorine has atomic number 17, so it has 17 electrons, and there are 2 chlorine atoms, so 17 into 2, plus oxygen 16, and there are 3 oxygen atoms, so 16 into 3. So that is 34 plus 48, which is equal to 82. Now ICl2 minus. So over here, iodine has atomic number 53. So therefore, there'll be 53 electrons plus 17 into 2 for chlorine for Cl2. and then there is a minus on top of it, so that implies -1. So this -1 represents extra negative charge, so extra 1 electron negative charge. So they have an extra 1 electron, so +1. So that is 53 plus 34 plus 1. That is equal to 88. So the first compound has 82 electrons and the second compound has 88 electrons. So therefore, these two are not isoelectronic. Let's look at option B. Now, ICl2 minus, we already know because we've calculated it once, so it'll be 88. Now we need to find out ClO2. ClO2. Chlorine 17 plus O2, that is 16. No, it's not 16 actually. It's 8 because one oxygen atom is 8. People usually get confused because they think of oxygen with atomic number 16. So I got with mass number 16. So I got confused between the mass number and the atomic number. For those of you who need revision, Z, that's the atomic number of oxygen, is 8. And A, which is the mass number of oxygen, is 16. So this is the quantity that we'll be taking here. So it'll be 24. 34 plus 24 is 58. So 17 plus 8 times 2. So that'll be equal to 17 plus 16, which will be equal to 33. So ICl2 minus is 88. ClO2 is 33. These are definitely not isoelectronic. Let's look at option C, IF2 plus and I3 minus. So IF2 plus. Iodine, again, 53 plus fluorine here has 9 as its atomic number. So 9 valence electrons. And there's 2 of them, so 9 into 2. And then since the whole compound has a plus charge, it means they are losing 1 electron. So it is 53 plus 18 minus 1. So that will be equal to 70. And I3 minus, now it has 53 times 3 plus 1 because there is a minus charge on it. So that will be 159 plus 1. That'll be equal to 160. So 70 and 160 are not equal. So therefore, option C is also not the right option. So from all of these, we can find out that option D, ClO2 minus and ClF2 plus, is the right option. But let's prove it so that we know that we got the right option. So ClO2 minus. Chlorine is 17 plus O2, so that's 8 times 2. And then there's a minus, so there's a plus 1. 17 plus 16 plus 1. So that is equal to 34. And then ClF2 plus. So that'll be equal to 17 plus F2 is 9 into 2. And then there's a plus, so that means minus 1 electron. So 17 plus 18 minus 1, which again is equal to 34. So for option D, since both ClO2 minus and ClF2 plus have 34 electrons, we can say that these are an isoelectronic pair. So option D is indeed the right option. Next question. The most probable radius in picometers for finding the electron in helium plus is equal to 0, 52.9, 26.5, 105.8. So over here, we're given that the unit is in picometers, and the particular species that we need to find out is He plus. So this has an atomic number 2, and the number of electrons is 1. So it will be in the first shell only. even if helium had 2 electrons, it would still be in the first shell because the first shell, that is the K shell, can hold a maximum of 2 electrons. So the energy level here is 1. So we need to find out the most probable radius for finding an electron. This is known as the Bohr's radius, and it is represented by the formula R is equal to 0.529 into 10 raised to minus 10 into n squared divided by z meters. Now over here, it is given in meters. We need to convert this into picometers. So 0.529 becomes 52.9 into 10 raised to minus 2. 10 raised to minus 2 into 10 raised to minus 10 will give you 10 raised to minus 12 into n squared divided by z meters. So that is equal to 52.9 into n squared divided by z picometers. So now we've converted the formula in terms of picometers. The step now is to put in all the values. So again, we have helium plus, so Z equal to 2, the atomic number, and the energy level of the electron present is 1. So R is 52.9 into n squared, so that is 1 squared divided by Z, that's 2. So 1 squared is the same as 1, so we have 52.9 divided by 2. So 529 divided by 2, 5, so 2 times 2 is 4, that's 1, 12, 6 times 2 is 12, so that's 0, and then 9, 2 times 4 is 8, 1, that becomes 10, so we have a point, and then 2 times 5 is 10, that's 0, so 264.5. And since our quantity is 52.9, so the decimal point moves 1 more unit left. So we get our answer as 26.45 picometers. So 26.45 can be approximated to 26.5 picometers. And if you look at our options, you find that option C, 26.5, is the right answer. Let's look at our final question of the day. The uncertainties in the velocities of two particles, A and B, are 0.05 and 0.02 meters per second, respectively. The mass of B is 5 times that of the mass of A. What is the ratio of uncertainties in the position of A divided by position of B position? So we have the ratio of uncertainties in the positions of A and B. We need to find that out. So let's write down the quantities given here. Uncertainties in the velocities of A and B are given. That is represented by delta VA. Delta VA is the uncertainty in the velocity of A, which is 0.05. And then for B, it'll be 0.02. Now, the mass of B is given as 5 times the mass of A. So let M is equal to mass of A. So therefore, mass of B will be equal to 5M. So we have the masses M and 5M. We need to find out the uncertainties in their positions and the ratio of it. So over here, we use the Heisenberg's uncertainty principle. So Heisenberg said that it is impossible to accurately calculate the position and the momentum of a particle effectively. So when we are getting the accurate position, the momentum will be compromised, and when the momentum is gotten right, the position will be compromised. And so this is represented in a formula. So that is delta X into M delta V is greater than or equal to H by 4 pi. Over here, for our question, we will assume the condition that delta x into m delta v is equal to h by 4 pi. So therefore, we can calculate the position delta x as h divided by 4 pi m delta v. So using this derivative, we can now find out the position uncertainties of A and B. Delta XA is equal to H, it stays the same. 4 pi stays the same. Now delta V of A, and that is given as 0.05, multiplied by the mass is given as m. And delta XB is equal to H divided by 4 pi times the uncertainty in velocity, that is given as 0.02, into the mass, that is 5m. So now our question is demanding us to find the ratio delta XA divided by delta XB. And that's precisely what we're going to do. So delta XA divided by delta XB. This is equal to H divided by 4 pi into 0.05 into m whole divided by H divided by 4 pi into 0.02 into 5m. H gets cancelled, 4 pi gets cancelled, m gets cancelled. So we have 1 by 0.05 whole divided by 1 by 0.02 into 5. That is equal to 0.02 into 5 divided by 0.05. So 2 into 5 is 10, so 0.02 into 5, that is 0.1 whole divided by 0.05. Multiplying 100 on both the numerator and the denominator, we get 10 by 5. So therefore, delta XA divided by delta XB will be equal to 10 by 5. 10 goes into 5 twice, that is equal to 2. So therefore, option A, 2, is the right answer for the ratio of uncertainties, delta XA and divided by delta XB. So that concludes this episode of NEET preparation. There are a lot of questions in NEET exams asking about the chapter structure of atom, and this has a wide variety of problems. So therefore, it's difficult to club everything into one episode. So we have made other episodes of structure of atom. Be sure to click the links in the description down below. And if you want to get more updates of our useful and interesting content, then please subscribe to our channel, Brain Blitz Audios. So we'll be back with more useful and interesting content such as mind maps, learner words, CBSE board exams, memory hacks, etc. So until the next episode, take care, stay safe, bye-bye for now.